Morning and welcome. Today is March 29th. This is actually the last class today in the month of March because on Wednesday we don't have a class, so we need to finish chapter 19 and then we really have to also get into chapter 20, and then we will have a spring break. After the spring break we will have our midterm. So here is the deal, okay? On Wednesday, although we don't have class, I'm going to try to record some problems from this chapter. And then when we meet on next week to do chapter 20, we're going to go basically introduce the second law of thermodynamics in chapter 20 and calculate basically the efficiency of certain engines. And then we delve into a lot of applications from chapter 20. It's going to be very important in terms of preparing you guys for the exam. So I'm really hoping that you guys are going to do all of the problems that we do in class and also follow the lecture and do all the examples and everything else so that you're ready for the exam. That is the exam review, okay? So there will be no special session dedicated to review, just to basically go through the things that we did go through per chapter, okay? We did chapter 12, then 15, then 16, all the way to basically right now we're finishing chapter 19. And then after that, we're going to get into chapter 20. And that's going to put us right midway where we need to be. After that, after the spring break, we will have our midterm. And then after that, we start optics. So this is basically, which is chapter 33, 34, 35, and 36. So basically 4 more chapters in addition to chapter 20, which we did not do. So this is in a nutshell how this course is progressing. At this point, we are in chapter 19. So let me share the screen so that we see where we are. Okay, so so this is what we did last week, okay? We did basically, we did introduce few processes. We introduced for a few concepts, the concept of work, which is, and I warned you guys about it, that this is how we're defining it. This is the standard way of defining it. If the work turned out to be negative, that is an indication that the system is losing energy, because this is basically the expression in its full glory. This is the first law of thermodynamics. First law of thermodynamics states basically that the change in the energy, in the internal energy of a system, be it gas or liquid, doesn't matter what it is basically the sum of two things. The amount of heat added to it or the amount of work done against it. So if the work is done against it, that means the volume is negative because it's being compressed. When the volume is negative, this whole quantity is positive, so it's going to be a net positive number added to the energy, to the internal energy of the system. Obviously, if the system is being heated up in a sense that heat is being added to it, then in this case also the internal energy of the system will increase. If anything backward, it's going to be basically a decrease in the internal energy of the system. Namely, if heat is being extracted from it, then in this case, there is a negative number in here. So therefore, loss in internal energy of the system. If work is being done by the gas, in other words, it's expanding, it moves things, okay? So in this case, delta P is positive because it's going to do work against the gas, or against its surrounding, I'm sorry. Then in this case, the gas or the system is doing work. This whole quantity then is positive because delta V is positive. The pressure is always positive, can never be negative. So in this case, this is positive, in which case this whole thing is negative. Obviously, in this case, the system must come up from the energy from somewhere to do work, and it must come from its internal energy. So this is basically how this is interpreted. And hopefully you guys see it this way. I don't like this convention that is used in the book to try to somehow argue that the negative sign in here, taken from here and put in there, will make sense. Okay, if you think that you can not go wrong with the convention of the book, use it. So this is basically the book. And I don't like the book about this one. And this is the standard convention. Okay. So that's basically how we're doing that. Again, so as long as you are understanding of what's going on, you shouldn't have difficulty with the science. So this is basically the first law of thermodynamics from chapter 19. After that, basically, we looked at the PV diagram. There are more than a PV diagram. There is the TV diagram where the temperature and the volume are represented, or actually the T diagram where the pressure and the temperature are presented. Typically, a lot of the times, at least a lot of these problems that you see in this class, including the lab, not today's lab, but the lab that is coming next week, also deals with the PV diagram, okay? The lab today is on the adiabatic process, which we're going to introduce today. Anyway, we introduced several processes. The first process we introduced is the isothermal process. In the isothermal process, the temperature doesn't change. Very, very important result. We discussed that the change in the internal energy is proportional to the internal change in temperature. Because this process is isothermal, then delta U is 0. End of the story. So in an isothermal process, isothermal means the temperature doesn't change. So that means delta U, which is typically NCV delta T, because delta T is 0, then delta U is 0. So we know that. Because of the first law of thermodynamics, Q plus W then must be 0. The heat added and the work done must add up to 0. In other words, if you add heat to the gas, it must expend to do work. So whatever heat you add to it, it's being lost in terms of energy for doing work. Or if the system is being compressed, namely you're adding actually energy through compression in this case, then the system must be exhausting heat somewhere so that Q plus W in an isothermal process stays 0. This is very important, okay? I know probably you're used to this stuff from your chemistry classes, and somehow probably you touched upon PV equal to nRT, and you thought that this is the whole deal. That is actually more than that. Actually, there is far more to it, and this is what the physics is. And I must admit that a lot of my students, basically, when they see that, when they see it from the physics perspective, they're kind of shocked a little bit. So I'm hoping that you guys follow the steps. Delta U, the change in the internal energy of the system, is basically N times CV, which is just a constant times delta T. If there is no delta T, there is no delta U, period. An isothermal process, by definition, there is no delta T. Does not change. Temperature doesn't change. Since the temperature doesn't change, the internal energy of the system does not change. In other words, however you cook Q and W, that must add up to 0. Q must be equal to negative W, okay? Since I can calculate what Q is, what W is, which is just in the integral, we have it all the way up in here, of PDV with a negative sign, the way that I'm following the standard convention, between some initial volume and some final volume, and use the fact that this is an ideal gas, PV equal to nRT. So this is where T doesn't change, so it's going to come out of the integral. R doesn't change, N doesn't change. So all of them, they will come out from the integral, and I'm left with dV over V, and that is just the ln. So I can find what W is, and indeed, if V1 is greater than V naught, this is actually going to be positive, greater than 1, in which case the ln is going to be a positive number, and the W in this case is a negative. In other words, during an isothermal expansion, the gas in this case does work, but heat is being pumped to it from this heat source, which is the isothermal source in this case. And you ask how much heat? Well, it's just the negative of that sign, whatever that sign is. If this is negative, then it's going to be positive. So that when you add the two numbers, is positive. It's going to be 0. Okay. Delta U is still 0. That is an isothermal process. Then we identified another process called the isochoric process or isovolumetric process. This is a process where there is no change in volume. Since there is no change in volume, there is no work done by the gas or done against the gas, because that involves dV. So if dV is 0, in an isothermal, in an isochoric process or an isovolumetric process, there is no work, okay? So the volume does not change. We're going through this line basically up through this volume, from this pressure to that pressure. So we're going increasing the pressure in here from P1 to P naught. Then in this case, hey, there is no change in the there is no work done. However, we're heating up the gas because this temperature must be lower from the starting point. Of course, if we're going through this process in here, we're heating it up from this temperature to that temperature. So in this case, heat is being added. In other words, energy of the internal system also is changing because we went from a lower temperature to a higher temperature. So in this case, the gas is actually gaining energy in the form of heat. Okay, so, and we defined in this case, CV, what is the, it's actually, it's always CV in this case. So it's going to be clearly Q is equal to delta U, which is NCV delta T. We define the molar specific heat at constant volume as being this quantity, okay? So where delta T is just a change in volume. So we can find these two quantities. Now we defined another process that was a little bit more involved and we didn't finish it honestly, is the isobaric process. The isobaric process involved, in this case, I went from volume V0 to volume V1. So the volume went up, increased in volume. So it must be doing work against the environment. Since the pressure is constant, it comes out of the integral, and I'm left with all is just calculate the integral of dx between an initial volume and a final volume, and that is going to be minus P0, which is constant in this process. Pressure is constant in an isobaric process. Then it's just a change in volume. So that is how much work is there. That is how much work is done. And it's negative because, again, we're losing energy in the form of work. Again, the gas is expanding. So in isobaric expansion, the gas does work in this case. So W is actually negative because it's losing energy in the form of work. However, heat now is increasing. Obviously, we're going also from a lower temperature to a higher temperature, and we defined CP. The molar specific heat, by definition, is this quantity. Okay, this is the definition of the molar specific heat, CP. Okay, so we have a CV at constant volume. This is a CP at constant pressure. Okay. And if you're wondering what happened to the entire energy, just the energy for the entire system is just the sum of these two quantities, Q plus W. Okay, wherever it lands, it lands. Okay. Obviously, it's going to be positive because the temperature in this case is higher. So delta U will be positive. In other words, there is a net heat higher because Q is positive. The change in temperature is positive. So there is a net heat higher than the work that the gas is doing. So yes, it's losing work energy in the form of work, but actually it's gaining more heat in the process. So during this process, that's what's going on. So I wanted to find a relationship between CP and CV, and let's see if we can do that, okay? Let's take a baby steps. Let's say, for example, we're going from T1, from T to T plus dt in an isobaric process. That means the pressure is not changing. Well, in this case, the energy changes by an increment that is from here to there. So the change in energy is going to be NCV dt, okay? The amount of work, so this is an isobaric process. The amount of work that the gas will do in this case is the integral, the finite value only. So we're not going to integrate. So it's going to be just the amount of work done in this process, which is minus PdV. P is constant. Okay, that is basically by definition what an isobaric process is. P doesn't change, okay? And then in the same process, we know that the amount of heat, so this is an infinitesimal isobaric process, okay? So dq, and because it's an isobaric process, is equal to NCP, the change in temperature. Okay, we plug everything and we're in business. Before we do that, let me remind you that PV is equal to nRT still. PV equal to nRT all the time. Because P doesn't change, I can take the different form in here during this process where P times dV is equal to nR dt. Why? Because P doesn't change in this process. So P times dV, P is constant. So the only thing that can change in this case from changing from the temperature to T plus dt is the volume. And the volume will change by an amount dV. So if the temperature is going up by an amount dt, the volume also has to go up with it because the pressure is constant. So this is the ideal gas law. This is true all the time. Now, we have several equations now. So we have the expression for du. We have the expression for dw. We have the expression for the heat. And this is basically by definition what the Cp is, what the molar specific heat is. And now we have the ideal gas law, which is equation number 4. All we need is just equation, the biggest one, which is just of the first law. So the first law in this process state that du must be just the sum of this heat plus the work. Okay? So we're going to plug everything. Du from equation 1 is ncv dt. ncv dt. dq from equation 3 is ncp dt. dw from equation 2 is actually equal to minus p dv. Okay? The only thing that we need to include is actually another equation, which is equation 4. And equation 4 gives me p dv, which is nr dt. So all I have to do is just include that in this expression, and then I have the following. ncv dt is equal to ncp dt minus pdv, and pdv is nr dt. So this is nr dt. Obviously, I took an arbitrary process, so the answer should not depend on it if I'm going to find the general relationship, and that's the whole point of this. Arbitrary change in temperature in this process, okay? So dt cancels, and dt cancels. It tends to be an isobaric process because we want to find what Cp is. That's all. So the dt cancels, and the n also cancels. So what we ended up with is Cv equal to Cp minus R, and this relationship is usually written in the following fashion. It's a very important relationship that you have to remember. Cp is Cv plus R. Okay, so this is a connection between Cp and Cv, and this is true all the time. No matter where you are, which system you have, this relationship is useful. Sometimes they give you just Cv, and you're supposed to find the rest. Okay, you're supposed to find Cp because you know R is 8.314. Okay, and most of the time they don't give you that either. They give you gamma, and gamma by definition, this is the gas ratio. It's the ratio of the molar specific heat at constant pressure over the molar specific heat at constant volume. So again, this is the molar specific heat. One of them, the first one at constant pressure, and the second one as constant volume. Okay. Cv, if you guys remember, was equal to 3/2 for a monoatomic gas, Cv is equal to 5/2 for a diatomic gas, Cv is equal to something else, usually around 7/2. This is not an exact now, okay, approximate for polyatomic gas. Cv is roughly equal to 3, or it's 3. This is actually an approximation too, because it needs actually quantum mechanics to fix it for a solid. Most of the time, this is the two types we're going to be dealing with. Monoatomic gas, like for example, helium, or an argon, or one of those noble gases, or a diatomic gas like carbon dioxide, I mean, not carbon dioxide, oxygen or nitrogen, which are the air. So the air is actually diatomic gas, or even the hydrogen in this case, which is also that, which is also the same thing in here. Okay, so from this relationship, Cp is Cv plus R divided by Cv. So gamma is actually equal to 1 plus R over Cv. So in other words, you can find what Cv is in terms of gamma. So So all you have to do is move R over CV to the other side, and you will have gamma minus, because CP is greater than R, greater than CV by an amount R, this gamma is always greater than 1. No matter what you do, it's always more than 1. Okay? Typical. I mean, it's not typical. It has to be more than 1. Okay? So that is something that you have to remember. So it's equal to, let's see how much it is equal to. CP, first of all, for a monoatomic gas, I have 3/2. I'm sorry, I forgot the R in here. There is an R everywhere, okay? There is an R in here too. There is an R in here too. There is an R in here too. So CP is actually equal to CV, which is 3/2 of an R, plus 1, which is going to be 5/2 of an R for a monoatomic gas. Whatever that number is, just add to it 1. CP is equal to 7/2 of an R for a diatomic gas. And CP is equal to what? 9/2 of an R for the other one, okay? For the last one, roughly, okay? 9/2 of an R. This is, again, an approximate for a polyatomic gas. Polyatomic gas is like, for example, carbon dioxide, okay? Or water vapor, okay? H2O. So those, they behave more or less like this one. So how much is gamma now? Gamma for all of these quantities is gamma is 5/2 of an R divided by 3/2 of an R for a monoatomic gas. That's the R cancels the R, the half cancels the half, and you'll be just left with 5/3. And this is 1.67 for a monoatomic gas. For a diatomic gas, it's going to be, again, 7/2 divided by 5/2. R cancels the R. So at the end, you'll be dividing 7/5, which is 1.4, which is a typical number for a diatomic gas, actually, for example, the air. Okay? And gamma is going to be 9/7. What is 9/7 now? I'm trying to put my calculator in here. 9/7. 1.3 roughly, okay? This number fluctuates, okay? Because there are quantum effects when you're reaching this much things in here for polyatomic gases. There are other vibrations involved, other degrees of freedom involved. So it's roughly about 1.3 for polyatomic gases. Most of the times gamma is given to you, okay? So you can solve now, if gamma is given, and you know what you can find what CV is from this relationship, okay? R over CV is equal to gamma minus 1, flip that one, so CV is going to be R over gamma minus 1, okay? And once you find what CV is, all you have to do is add to it another R. The common denominator is gamma, so it's going to be gamma R over, so CP is just going to be gamma R over gamma minus 1. So basically, gamma can if you know what it is, you can find what the gas, what the other quantities are. Furthermore, I lost my train of thought in here about the CP and C gamma, everything. Okay, the other thing, that is the point in here I'm trying to reach to. If you don't know what the gas is, and you somehow go to the lab and do an experiment and find, for example, a gamma, and you will find it to be 1.67. So you know specifically you're dealing with a monoatomic gas. If you find it 1.4 or roughly around that number, you know you're dealing with a diatomic gas. If you find it around 1.3, that means it's neither of the two, okay? So, and that is basically how we're going to be handling these problems from this point on, okay? So this is something very important, and how gamma is now important for us, okay? And this is what the lab this afternoon is about, gamma, actually trying to find what gamma is. So the last process of the 4 processes that I promised we're going to be doing is, I'm sorry, the 4th process is the adiabatic process. In this process, basically Q is equal to 0. So that means that if I'm computing the change in the energy will be just simply the amount of work that is done. End of the story. This is the amount of work. This is W in an infinitesimal process. So here is the deal. You have a gas, I'm going to draw the PV diagram again. So we have a temperature T1, for example, and we have another temperature T2 in here. And the gas goes from the first state, initial state in here that has well-defined values. Let's call it V1 and P1 at sitting at temperature T1 and ends up somewhere in here with a different volume V2 at a different pressure P2 with a temperature T2. So in here, this is a point in space in the PV diagram that is all of the values change. The pressure, the volume, and the temperature also, and the energy also. Everything changes, okay? And in this case, it's V2, P2, and of course, this is a point on PV diagram, but also T2, which is given that P2, V2 is equal to nRT2. And this point in here in space is P1, V1 is equal to nRT1, okay? And there is no heat change. Q is equal to 0. That is what an adiabatic process is. You take the whole thing and put it in, wrap it in a blanket, basically, and put it hidden so that it doesn't receive or give up heat. And so basically, it's well wrapped. It's well wrapped. So in this case, this is what the adiabatic process is. This is a process with no change. This sometimes is called an adiabat, okay? This line itself is called an adiabat. So we really need to find the expression on how P depends on V in here. P is a function of V. Function. If we want to find, for example, this integral, if we want to find what the work is, because the work is going to be this integral minus the integral of P as a function of V times dV from some initial volume V1 to a final volume V2. That is actually going to be the work. And that is going to be also the change in energy, because there is no heat exchange in this process, okay? Now, we need to find this function. If we find this function, then we can do this integral and do a lot of things with it. So we need to find how P depends on V. So let's go and analyze this process again on an infinitesimal process. On an infinitesimal process, the gas goes from a temperature T to a new temperature now, T plus dt. In doing so, its energy changes by the amount again, NCV dt. And if I analyze the PV equal to nRT, because it's still an ideal gas, now I cannot say that just P doesn't change. This is not an isobaric process. So PV equal to nRT, when the temperature goes from T to T plus dt, both P and V change. Because as a matter of fact, the whole P and V change from initial values to final values. So I cannot say that, like I did earlier in the process of the isobaric process, that I just ignored the change in P because there was none, because it was an isobaric process. So when the temperature changed on the other side is just nR dt. When this quantity changed on both sides, so it's going to be either PdV or plus VdP. Okay. So this is how you compute changes in quantities where the two variables can change, okay? So this is in this process, in going from this temperature to this temperature in this process, adiabatic process, where there is no heat exchange. So dq is equal to 0 still, okay? So there is no change in this process. So when I say that, what I mean by that is the ideal gas law now can be written, I'm sorry, the second law of the first law of thermodynamics state that the following, that in this case, just P equal to minus PdV, okay? Why? Because dq is equal to 0. All the change in the energy is coming from work, end of story, because there is no heat exchange. So if we do that, let's see what we're gonna get. On one side, it's always true that du is equal to ncv dt, okay? The only trouble with here, I have PdV, okay? So what I'm going to do in here, I'm going to take this expression where it has nr dt and find what ndt is. So let's write this expression in here again, because I need it in this expression. Because my goal is to find P as a function of V. So I need to get rid of dt. So eliminate, oh man, what happened to my? If it crashes on us, please stick around, okay, don't go. Eliminate dt, because Our goal is to find P as a function of volume, okay? So that we can plug it into this expression and do the integrations and do stuff for us, okay? So because we're doing actually a PV diagram, and T is changing in this case, so T is not fixed. P is not fixed. V is not fixed. Nobody's fixed. Everything is changing. The only thing that is not changing, or at least no exchange of it, is the heat. That's all. Okay. So we're going to get rid of dt from one of these expressions. So I'm going to write this equation as equation number 1. And this is equation number 2. So using equation number 1, we're going to find, because we already have ndt in here, we need ndt actually. Ndt from that expression is going to simply be equal to, or use equation number 2 instead, it's easier. Okay, let's use equation number 2. I'm sorry about that. So let's do ndt from equation number 2 being minus p dv over cv. So now we take this value and sub it in equation number 1. So when we do that, this is what we're going to end up with. And then we will not have dt at all in our expression. So the first side of the equation is just p dv plus vdp is equal to nr dt. So, and I have n dt in here. All I have to do is multiply this expression by r, and we're in business. So it's minus r over cv times p dv. Okay. So this is the expression that we ended up with. Now I don't have dt whatsoever in this expression. All three of them are changing. But in this expression now we use the ideal gas law to get rid of that dt in here. So now I have a PdV and I have a PdV, and I have this factor of negative R over CV, which I'm going to bring it to the other side. It's going to be positive. So we're going to pull PdV as a common factor. So we'll be left with 1 on this side plus R over CV times PdV plus VdP is equal to 0. Okay. 1 plus R over CV, isn't that gamma? That is exactly gamma for the ideal gas law. Okay, for the few of you who came in late, you probably need to watch the first half. We did a little bit of a review on the stuff that we talked about last time. And we found a relationship between CP and CV, which is a very important relationship, this one. So you really, really need to come back to this discussion and understand it. As a matter of fact, this is going to be the item of discussion that you need to list the different values of CV for different gases in here, and also CP. So list CP, CV, and gamma for different gases, basically for a monoatomic gas, for diatomic gas, and for polyatomic gas, and even for solids, okay? So for that, you don't really understand, there is no clear expression for CP in that case, okay? So don't use it for solids in there, okay? But this is basically the expression that we need to come back to, and we defined gamma as a gas ratio, not ration, okay? As being the ratio of the two molar specific heat, CP and CV. And then we are now in the process of finding another process called the adiabatic process. In the adiabatic process, there is no heat exchange. So we're trying to find now, because everything changes in the adiabatic process. Temperature changes, volume changes, and pressure changes. So there is nothing of that luxury that we were doing with the first 3 processes. Isothermal process, temperature doesn't change. Isobaric process, pressure doesn't change. Isovolumetric process, the volume does not change. In this case, everybody changes of the first 3. The only thing is there is no heat exchange. Q is equal to 0. So in doing so, we're trying to find now a relationship between how P and V change, because we're using the PV diagram. If we're using the TV diagram, we're going to find how T and V depend on one another. And that's important too. Okay, and we're going to do that too. It's going to be a very easy thing. Actually, it's part of the lab too. So this is gamma. So what we ended up with, gamma PdV plus VdP is equal to 0. I'm going to condense this expression a little. This is what we're going to do. So we're going to divide by PV. So multiply everywhere by PV. So the P cancel the P in here, and I will be left with dV over V. So it's going to be gamma dV over V plus V cancels the V, and the second one I will left with dP over P is equal to 0. Obviously, if I integrate both sides, this is going to be a constant on one side. The integral of 0 is constant. The integral of dp over p, that is just the natural log of p. And the integral of dv over v, that is actually the natural log of v. And that is the expression in here. Gamma times the natural log is equal to the natural log to the power gamma, that's all. So this is ln of v to the power gamma plus ln of p is equal to a constant. Now the sum of the ln's is the ln of the product. So this is an ln of pv to the power gamma is equal to a constant. And when I exponentiate again, the ln goes away and the exponential of a constant is just another constant, okay? So pv to the power gamma is just another constant, not necessarily the first constant, it's just another constant, that's all. As a matter of fact, I can find what that constant is. Let me tell you, we started from this point on PV diagram, V1, P1, and we ended up in V2, P2. So what is that constant? It could be just any of these numbers. P1, V1 to the power gamma, that is actually the constant. So this, because this is part of the same adiabat, the same line in here that is described by this equation. Okay, as a matter of fact, since we know the point V1 and P1 are part of this line, then we know that P1 V1 to the power gamma is constant. So that is how much that constant is. As a matter of fact, we can find it differently too. We know that V2 P2 is also part of the same diagram. So that too is P2 V2 to the power gamma. That is the same constant. In other words, P1 V1 to the power gamma, P2 V2 to the power gamma, and any point P in this adiabat line satisfy this equation. So that's how you draw this one in here, where gamma is more than 1. I made a big argument earlier about it because gamma is the ratio of Cp over Cv, and Cp is always greater by R than Cv. So this ratio in here must be greater than 1, and this line actually goes faster to 0 than the isothermal. That's why sometimes this is called an adiabatic precipitation, because the gas goes through very rapid, in this case, expansion on the adiabatic line. Okay, so this is in a nutshell what the adiabatic process. Now you're asking, okay, you gave me PV on the PV diagram, and these parts of the questions that you're going to have in the lab too, actually. On a TV diagram, how are we going to do that? Okay, remember, in the TV diagram, the volume is just equal to, what is it? nRT over P, where P now is the slope of this line. So it's going to be slope lines like this one, okay? They're all passed by the origin, by the way. Sorry, T is from 0 Kelvin in this case. This is hardly used in this case. If it's 0 Kelvin, it's passes, if it's degrees Celsius, this extends to infinity and to a negative 273, okay? So, because there is a y-intercept then. Because if T now is in Kelvin, this lines, all of them merge to the x-axis. It doesn't matter. So now I want to find that relationship. So we know that PV equal to nRT, and we know that PV to the power gamma is a constant. So all I have to do now is express P in terms of T. And P in terms of T is just equal to nRT. So this is basically what P is, over gamma. I'm sorry, over V. So all I have to do is just take this expression and plug it into the equation. So what I will end up with is nR times T times V to the power gamma divided by V is equal to a constant. Divide by nR, which is just another constant. So the constant will change in this scenario. And it's going to be TV to the power gamma minus 1 is equal to a constant, where that constant is just basically the new constant, not necessarily the first constant. It's the old constant divided by nR, okay? Which is just another constant, number more than in this case the constant R, okay? So that is basically how you do it. And same thing, if you're going to use, for example, a PT diagram, then in that case you get rid of the volume using the ideal gas law. So you use the volume equal to nRT over P, and you sub in this expression, and you will have P times some nRT divided to the power gamma divided by P to the power gamma, and the expression now will have a P and a T in it, and everything else will be just pushed into the other constant on the other side. And there is gamma always involved in there. So I hope that you can do it. It's part of the lab. We're going to have a more discussion on that one. But this is basically, in a nutshell, what this whole idea is. Have you seen this process in chemistry for those who took chemistry class? The adiabatic process. Or have you, this is the first time you hear about it, even if you took chemistry or you didn't take chemistry? Come on, guys. Is this the first time you hear about the adiabatic process? In school, of course. I don't mean outside of school. Okay. If this is the first time, and I'm glad that at least one of you guys is replying in here, you really have to get used to it. You really have to get to understand it, because it's going to be critical, first of all, for the lab. The entire lab this afternoon is all about it, okay? And then also the next lab also will deal with it. And the exam will deal with it. And the examples we're going to calculate are dealing with it. The gas engine, I think problem 47 from the next chapter, chapter 20, is about VW, Volkswagen basically, engine, which uses the Otto cycle. And the Otto cycle has 2 adiabatic processes. It's actually 6. It's an Otto cycle, and the Otto cycle is applicable for all cars, okay, like the light vehicles. And it involves two adiabats. It's a 6-stroke engine during the gas intake. That is actually an expansion, in this case, at constant pressure. And then it goes through an adiabat, followed by an isovolumetric process, where there is no work done at that point. There is only heat coming to the gas during that compression. And then another adiabatic, in this case, expansion, where the gas is actually doing work with no heat exchange. And then finally, another compression, basically a change in pressure, but no volume change. Again, it's an isochoric process, back to where we started from, to the starting point, and followed by compression, in this case, to the initial point during the exhaust stage, basically, where they get rid of the gases. And then another intake of basically gas combination with air, combustion. So this is basically, it's a 6-stroke engine. It involves 2 adiabats. Diesel engine also involves 2 adiabats. The diesel engine is a little bit more different, in a sense, still has the 2 adiabats similar to the first one, compression and decompression. And also it has a cycle, a process of involving the isovolumetric process. And then instead of another isovolumetric process, it involves an isobaric process. So that is the diesel engine usually used for higher, for more, how should I say it, heavier components like trucks and heavy machinery and all of that, okay? And then the Stirling engine, which is really has no industrial application, is just used for, and we're going to demo that. I have it actually in here, the Stirling engine. The Stirling engine uses it's a 4-stroke engine too, and it uses basically 2 isovolumetric processes in here. The volume does not change, followed by 2 processes at constant temperature, okay, 2 isothermals. So this one does not use an adiabatic process, but the Otto engine uses the adiabatic process, and also the diesel engine uses an adiabatic process. Now the ideal gas law, the best engine there is a Carnot cycle, Carnot engine, okay? The Carnot engine, which is part of the next chapter big time, uses actually also 4-stroke engine, and it uses 2 isothermals and 2 adiabatics. Okay, so the adiabatic process also is there too in the Carnot engine. There will be a lot of problems on Carnot. There will be at least another problem on Otto engine, OTTO, not AUTO. Okay, Otto, that's the person who discovered it. And the diesel engine, probably, I'm not sure exactly on a diesel engine, but for sure on the Stirling engine, although it's a good model, but it's still at this point not really, there is no real industrial applications for it. So that is basically how these things are. Okay, What do I need to do? I don't care about what you're talking about. All I care about is just to pass physics 4C. Okay, so what's the bottom line? The bottom line is in an ideal gas law on how to solve my problems. Let me share with you the screen. What you need to remember is PV to the power gamma is constant. In an adiabatic process. Adiabatic process. Okay. Probably I don't think we did, but from chapter 15, when we were calculating the sound and Mr. Newton assumed that it's some sort of an isothermal process, it turns out to be not an isothermal process, it's actually more of an adiabatic process. And that is where that gamma, if you guys remember, came into the expression in the velocity of sound. So it's gamma RT over, what is it? I forgot the denominator, mu or rho or something like that. So that's where the value is coming from. It's coming from here, from this adiabatic process. So it's a very important process that you really need to get accustomed to. This is a process where you take the system and you wrap it in good sealing so that it does not lose heat or gain heat. Like, for example, thermos. Okay, so in this case, it's an adiabatic process. Put it inside big blanket so it does not lose heat or gain heat, then it's an adiabatic process. So this is the main thing for it, and that's really what should get you going through the problem. What gamma is most of the time given to you, or you're going to calculate or measure it like we're going to do later on in the lab today, okay? So this is in a nutshell chapter 19. I want to introduce chapter 20. As I was saying before, some of you joined us earlier. On Wednesday, we don't have class because of the fact that it's a holiday, and I really want you guys to enjoy it. But what I'm going to do also is probably do light problems, record them, maybe 2 or 3, because typically, honestly, I don't do a lot of problems from chapter 19. I reserve them for chapter actually 20, because these processes are identical. When a system goes through a process and another process, and come back to the starting point, it becomes a cycle, okay? So in that sense, this is basically what chapter 20 is. And it's really, chapter 19 is feeding everything into chapter 20. And chapter 20 is the culmination of all of this stuff. So I'm going to have a few problems recorded for you guys, maybe 2, 3 at most, and then reserve a lot of the application for chapter 20. Does this sound like it's a good plan? Yes, no, maybe. Okay, very good. How is everybody else? Okay, very good. No, I'm glad to hear from you too. Okay, so let's share the screen and introduce chapter 20. And we're gonna call it today. So actually we need the new page for it too. CH20. Okay. So we know about the Zeroth Law. That's what allowed us actually to measure temperature. Basically, this is what the Zeroth Law is. It says that you have a system A, and you have a system B, and you have a system C. It says that if system A and system B are in thermal equilibrium, and system C and system B are also in thermal equilibrium. So this is a condition, not a... So you need to check on it. Are they? So if they are, then the first law says that these two also are in thermal equilibrium. Thermal equilibrium means that if I feel them, they have the same feel to it. They have the same temperature, really. So if this system A and system B has the same. So this what did for me, it allowed me actually to define what the thermometer is. So I can take, for example, take for system A being the water and see where it's going to freeze and call that one on this scale, whatever scale you like to call it, 0 or 32 degrees, that's fine. And then see where it's going to boil and call this one 100 degrees Celsius or 212 degrees Fahrenheit. And then start divisions in here. Every time I mount an amount of heat in here to it, the temperature is rising, obviously, and I can feel it too. And I can graduate this one. Hopefully it stays linear with it, where the specific heat in this case does not depend on temperature. That means it's constant throughout this entire process. That allows for this linear divisions to be more and more uniform. And now I have a thermometer gauged with system A. Take this thermometer now and put it in thermal contact with system C. Another one, doesn't matter. And once it reaches equilibrium, for example, this one reads, for example, 27 degrees Celsius, okay? So in this case, I can say that this temperature is 70 degrees Celsius. So what does it mean? It means the temperature the amount of heat I have to add to water to reach this temperature on this scale. So that temperature now is a representation of that heat that was added to the system to reach this temperature. So that is basically what the first law does for me. It allows me to invent the thermometer and carries it with me. And from this point on, we have basically a way of finding the temperature. Okay, so we have that equation. Now we moved along. We saw that experimentally PV equal to nRT. And we also justified it through the work of Mr. Boltzmann, that PV is basically proportional to the average. So this is on a molecular level. It's the average of the kinetic energy of the molecules, okay? From here, since this is PV and this is PV, so the temperature and this ones, they are proportional to one another. This is not exactly, but proportional, okay? There is a big N in here, the number of molecules that is coming to it. So we need the big N in here times kBT, okay? Where kBT now is actually equal to 1/2 of mv squared. Actually, there is 3 of them, okay? So there is 3 degrees of freedom in here. So the kinetic energy in this case for a single molecule turn out to be, 3/2 of kBT, okay? So each degree of freedom, because the molecule can move in the X direction and the Y direction and the Z direction. So this is in a nutshell what we ended up with. And now if I multiply this one by big N and define the Avogadro's number and the relationship between KB and R, that is basically how we found that relationship between Boltzmann constant and the ideal gas constant, okay, R. So from there, we have a relationship between them involving Avogadro's number, and we take this expression now for that. Now, the internal energy is what that energy of the gas is. So it turns out now, this is true only for monoatomic gases. For diatomic gases, there is another additional amount to the energy coming from rotation. There are 2 more degrees of freedom for a diatomic gas, and there are more degrees of freedom for polyatomic gases. So that's why this number kept on changing on us. And we found du in general is equal to NCV dt, okay? We came with the second law, with the first law of thermodynamics, and the first law of thermodynamics tells me basically that this is true all the time, okay? I took it in an infinitesimal process, but it's true even on a finite process where the change in the energy is equal to the amount of heat plus the work that is done against the gas. So this is the first law of thermodynamics. It's really conservation of energy, no more. Okay. Obviously, this number can be positive or negative. What we have so far is the following. Let me take a PV diagram to understand what's going on with it, okay? Here is the PV diagram. I have the volume, and I have the pressure. Man, I cannot draw a straight line up. Can you do it differently? Maybe if I could come from the up coming down. Still tilted, I'm sorry about that. Okay, this is the pressure. Okay, so we're taking a point in space in the PV diagram. That point has a specific value for the volume and specific value for the pressure, okay? So these are state variables, V and P are state variables. As a matter of fact, T also is. So if you're wondering what T is, it's just NR. Sorry, it's PV over NR. So we know what T is. T also is state variable. We're saying we have a state variable also, which is the energy U in this case. That is also a state variable because it only depends on T. So if T changes, U changes. So that is actually also a state variable. So this is so far the state variables. Q and W are not state variables. What am I talking about in here? What I'm saying is the following. If you give me a specific point in the PV diagram, I know exactly how much volume it has, how much pressure it has, how much temperature it has, and how much energy it has. We really don't care usually about the energy, we care about the change in the energy. In other words, if the system goes through a cycle, it comes back to this point, there is no change in volume because it came back to a starting volume. There is no change in pressure because it came back to the starting point. In pressure. There is no change in temperature because my final temperature, my initial temperature are the same. There is no change in energy. Delta U is 0 throughout the cycle because, again, it's a state variable. However, it may be doing work, and the work actually is equal to the integral in here. So this is the area. So the work in this case is not 0. It depends actually on the path I take. So for example, if I took this process, I have this amount of work. If I took and this is actually going clockwise. So this is actually a negative work. So this is actually an engine. This is an engine because I'm going clockwise. You saw it, okay? But if I do this cycle now instead, going like this, it doesn't matter how, as long as my ending point is the same. This is the work now. So I'm going this way now. It's this area, and there is an overlap in here too. That needs to be canceled, okay? Because I went through it once. So if this is like this, so this is actually outside of the integral. So this is the amount of work, the red one, but that is actually a heat pump, like a refrigerator. So the red one is not an engine. I'm going counterclockwise. So the red one is actually a heat pump. I'm pumping heat outside, so it's like a refrigerator. That's what the refrigerators do. They take heat from something that has cold and they pump it out. So this is what is the convention for the name for a refrigerator. It's a heat pump, okay? It takes the heat and gets it outside of basically the system. So that's a refrigerator, actually. That's what the common name for them is. Okay, but this one, the work now is actually going to be positive. So in other words, there is an added energy to the gas in this case. Okay, added energy to the system. Okay, added energy to the system in the form of this work that I'm going to add to it. So I want to understand these two kinds of cycles. So there are two kinds of cycles that we really have to worry about, to worry ourselves about them. An engine, which is going to be the focus for everything in here, is the one that is going to go through a clockwise cycle. A heat pump is going to be the reverse of that, okay? Mr. Carnot, and everybody actually was interested in, especially the engines, and wanted to know what is the most efficient engine. So Mr. Carnot, Sadi Carnot, asked the following question: what is the most efficient engine? In other words, an engine that can give you a bigger area, a lot of work for very little cost. Okay, so that is in a nutshell what the question is. So he wanted to know the most efficient engine. So we define the efficiency in this case is the amount of work that you're going to get from the engine. I'm taking it in absolute value because it's going to be, in this case, negative value, okay? Negative area. Divided by the cost. In this case, you have to have something hot to extract energy from it and actually get it into work, okay? So that is the cost. If you wish, the burning of fuel inside your engine is the cost, because you're going to pay for that fuel. You go to the pump and you put that fuel in, and you're going to actually pay for it. Physically speaking, not figuratively. You're going to actually pay for that one. So this is basically, so the amount of heat you add to the gas, that is your cost. And what you want from an engine is work. You want to do work. In the case of refrigeration, the process is a little bit reverse, okay? The process works in a different fashion. You have to actually do work to remove heat and dump it outside. So it's actually a reverse engine, if you wish. So that's why we don't focus a lot on the refrigeration or heat pumps, because actually they're just a process backward. Here is how the picture you can imagine it. This is how the picture you can envision it, at least in your heads, okay? You have a source of heat sitting at temperature T hot. You have a cold source sitting at T cold. An engine has to operate, at least a thermodynamic heat engine has to operate between two temperatures. You cannot have an engine that operates without them. And this is actually a condition that Mr. Carnot has to state, okay? That if you say the following, if you have T cold and T hot, and grant me the following, he said, allow me amuse me with this idea, that heat by itself cannot spontaneously go from a cold source to a hot source. If I take, for example, a cup of coffee that is hot and put it on the table, it's not going to get hotter after a while. And the room is not going to get colder after a while. Actually, the heat will flow from the hot coffee to the room. And the cup of coffee, if I come in a few minutes later or a few hours later, it's going to be basically room temperature. So it's going to lose heat in that fashion. So heat, he says, if you allow me this exception, that no heat can travel by itself from a cold source to a hot source. From a hot source to a cold source, it can. And that is what observation has shown. You can always see something hot becomes colder. As a matter of fact, if you take, for example, an ice cube from the refrigerator and put it on the table and wait, heat does not spontaneously travel from the ice to the room. It travels from the room to the ice and makes the ice hotter and actually starts to change into liquid. Now, could it be that if I take, for example, an ice, or at least, for example, some water, and put it on a cup, and put it, for example, in an afternoon, in a July afternoon, and put it outside, and come for it, for example, half an hour later and find it ice cold, becoming frozen? That's not possible. That is not possible. Heat does not travel from a cold source to a hot source on its own. And this is exactly what the role of refrigerator is actually doing. You take, for example, something cold, and you put it in the refrigerator, it makes it colder by removing heat from it. And that is actually the reverse of an engine. That is actually a refrigerator. That's its job. And the process there is defined by the performance of a refrigerator. Performance of a refrigerator is a desirable thing in this case, which is the cold. You want it to be colder. That's why you set up your refrigerator to a lower temperature. Or actually the same thing is happening actually with the AC unit. You want your room to be colder and colder, but that's going to cost you energy in that case. So the cost in that case is the energy that is going to be that you need to do this per se. So again, you can define these quantities. That is called the coefficient of performance for a refrigerator. In this case, is going to be the efficiency. He said the following. So in this case, what we're doing in here, we're taking heat from the hot source. So we're going to call this one QH. I'm going to take it in absolute value because I know it's going to be actually positive in this case. We're going to dump in the process heat into the cold source. It has to work this way, okay? It cannot work any other way. Obviously, QC in algebraic value is going to be negative value, so if we compute it, it's going to be negative. But I'm taking it in absolute value because I'm already pointing in the directions in which way it's flowing. So the gas in this case takes heat from the hot source and dumps it, some of it into the cold source, and the difference between them is going to be the work. So this is actually the work that I'm going to get from this thing. If the system goes through a cycle, it's going to come back and do this again and again and again and again and again every second. every time the cycle repeats, basically. And we have now an engine working at constant rates in this case. As long as the hot source is still hot, you can still work with this engine. There's no problem with it. Now, if you run out of energy, then that's a problem. The engine stops from working, and that's the end of it. So this is basically how the whole setup is. So Mr. Carnot asked the question, what is the most efficient engine? Describe it in this fashion. So he wants E to be as high as possible, okay? What you will see in this chapter is the fact that E can never be equal to 100%. In other words, there will be always QC. This difference, of course, is, I mean, the first law tells me clearly that Q hat is the sum of these two, the incoming and this is the outgoing. So Q hat is just simply the sum of QC plus W, in this case, the net work that we're going to get from it. And the work is going to be just the difference of these two. So you can write it backward in here, and it's going to be just 1 minus QC over QH. In absolute value. Again, QC is negative, so that's why I take it in absolute values. If I don't take it in absolute values, this will be a plus, and of course the QC will turn out to be negative in this number. But I'm illustrating it in here with absolute value to understand that E is always less than 1. Usually it's expressed in terms of a percentage value, okay? 20% efficient, 50% efficient, 75% efficient, 99.9% efficient, but never 100% efficient. Okay, it's always going to be less than 100%. So that is basically the bottom line that we're trying to get into in here. So actually, this is what I'm saying in here is actually the second law of thermodynamics, that heat does not spontaneously travel from cold source to a hot source. I mean, it can travel the other way, that's fine, but not spontaneously on its own without help. Okay, so if wondering how the refrigerator look like, it's just the reverse of that one. So it takes work and extracts heat from the cold source and dump the excess in here into the hot source. So it's working against the first law, the second law of thermodynamics. So it's that process reversed. This is what so this is an engine. Okay, and the coefficient of performance in this case has to do with the desirable thing, how much heat you're going to take, versus how much it's going to cost you, W, in terms of energy, okay? And that is going to be the process defined backward, and that is the coefficient of performance in this case. So this is actually not an engine, but a refrigerator. It's just a process looking backward, okay? A heat pump, okay? Or an AC unit, it's the same thing. AC unit, it pumps heat outside of the room to the outside environment. So that is basically how this is working. So this is actually in a nutshell what this whole thing is. So let's look at some processes. How much time do we still have? Okay, I'm going to explore the Otto engine since I mentioned it before. And we're going to come to the most important engine of them all, which is the Carnot engine, okay? So in an Otto cycle, as I mentioned in the beginning that it's a 6-stroke engine, but actually you can, the first two, they cancel, at least in the calculations, they cancel one another completely. So as I said before, so there is a volume in here. This is the second volume, I'm gonna call it V2. This is actually the starting volume V1. I'm gonna draw a line in here, completely perpendicular to that line in here. And this one also is perpendicular to this side. This is my starting volume, okay? So the ratio of V2 over V1 is by definition the compression ratio for an Otto cycle. So this is the Otto cycle. This is the one that is used in cars, light cars, okay, light vehicles. So in other words, V2 is RV1. So this, during the intake, you go through here. During the exhaust, you come back in the opposite direction. So this is actually the starting point. But because these two, they cancel, we're going to focus only the main parts of it, which is where the work is going to be done. So we're going to go through an adiabatic process from this point. This obviously has a pressure P1. I'm going to call this point A first. This has the pressure PA. Let's call it PA that way, okay? Obviously, the temperatures are not the same, so I'm going to talk about the temperature. Then you're going to increase the pressure. This point is going to be B, okay? So this is the pressure in here, and the volume is V1, but the pressure, I'm going to call it PB. And then you increase the pressure up to a certain pressure level in here. At this point, I'm going to call it C. So this is PC. Then you're going to come down to another point on another adiabatic process. Okay? On another adiabatic process to a point D. So this point in pressure is going to be PD. Okay? So many things to look at in here. So this is actually the 4 cycle versions of it, the 4 strokes of it, not the 4 cycle, the 4 strokes, the 4 processes involved in here at this point. So Q is equal to 0 in this case. Q is equal to 0 in this case. Both of them are adiabats. In this case, W is equal to 0 because this is constant volume. But QH is not 0. Actually, you can clearly see that the temperature in here is, we went from a lower temperature to a higher temperature. That means that we're heating up the gas. We're adding heat to it. So this is where QH happened. During this cycle is where actually we're getting rid of heat in this case. We're going from a higher temperature to a lower temperature. So this is where QC is. This number has to be negative. Okay, so we're intaking heat in here in the form of QH. And we're getting rid of heat in here in the form of QC. There is no work in here either. Okay, that is equal to 0 because again, the gas is coming at constant volume, V2 in this case. Okay. Now, Q is equal to 0, but W in this case is positive because we're going from a higher volume to a lower volume. So we're compressing the gas now. So in case W in here is actually positive from A to B, WAB is positive. WCD is actually negative. Why is it negative? Because we're expanding, the gas is expanding. And it's actually more than this WAB, okay? Because it's the area around this shape, and the other one is the area around this shape, which is actually a bigger area, as you can clearly see. The boundaries are the same, and this is sits the higher points on the curve in here. So actually, this is where the two works are. Now, one of them is higher than the other one, and the higher is negative, so the net work is going to be negative. So this thing is going to do work for me. That's why it's an engine. So actually, this is where the W net is. And it's a negative number. Because I'm going through this cycle in this process from A to B, from B to C, from C to D, and from D to A. What happened in these 2 stages in here are irrelevant as far as the cycle and work calculations and everything else, efficiency and everything else. Does this point make sense to you guys? Does this description, at least of the cycle, did not do any calculation, but I'm just describing the 4 different processes in this cycle. We have 2 adiabats and we have 2 isochoric processes. That take us back to the starting point A. Does this make sense? And it's very important that you guys pay attention to the science too. It's very, very important because everything is exactly how I was describing it before in terms of the work in and work out. And so let me go back into an engine. So we have QH. Where is QH in here? Here is QH. It's coming to the system. When we went from a lower temperature to a higher temperature, the pressure went up. The volume stayed the same, and PV equal to nRT all the time. Since the pressure went up, the temperature went up. In this case, it's the opposite. The temperature went down because the pressure went from PD down to back to PA. And this is actually the temperature went down because PV equal to nRT. Since the pressure went down, TA went down, okay?
But W is equal to 0 because W has to do with the change in volume. And we made an argument earlier from chapter 19 on the fact that the work in the case of an isochoric process is 0. So in this case, the change in the energy is just the heat. And this heat is positive and this heat is negative, okay? Furthermore, there is no heat in an adiabat. These two have no heats in them. So that's why it's kind of simple to some extent, the Otto engine, okay? Simple in terms of concept, actually, because there is no heat in here. Q is equal to 0, but there is W for sure. And W, because we're compressing it, the volume is shrinking down by a factor of R. This is the compression rate. This is the compression rate by definition. This is a characteristic of the engine, the manufacturer of the engine, and they give you a specific for problem 47 from this chapter on the VW car and how much VW actually Jetta, to be more specific, and how much R is and all the specifics of that engine so that you can work realistic numbers for that one. And actually they give you the size of the cylinder, how big the diameter is, and how when the piston is fully extended, how far is it from basically when it's not fully extended. So how much it travels basically in and out. So, and those are, what is it? They have a name for them. I forgot what they call them in mechanical engineers. So that has all of the stuff that is from that one. So it's a VW Jetta specific engine, okay? So if you have one of those cars, you know exactly, at least this model can represent that calculation. So this is basically the network, and the network is going to be negative in this case because it is actually a clockwise cycle. Okay, that's why I really like this convention, the standard convention, better than the book, because everything fits in the picture. When you're doing something clockwise, it has to be negative. And negative in a sense that the gas is actually delivering work to you. The mixture of air and fuel in this case is actually doing work. And that work is where the car is moving actually. So that is the stuff that you can clearly see. So where is that work coming from? It must be coming from the energy of the gas, okay? Obviously you're paying for it in the gas station because you have to put that fuel in to begin with, but that's another story. It's still coming from the gas in this case, okay? That you bought it with your own money. So it's still, this whole thing makes sense. Okay, like I said, there are two stages, two strokes in this engine that I'm not including in calculations because they don't matter, at least in terms of the efficiency. And they are actually the intake going from this stage, if you want to call it A, B, C, D, E, if you want to call it E. And the first stage going to A and then coming back on the same line A to E during the exhaust stage. And those are just I mean, if you look at the cylinder, it has two openings, okay? One, when the gas is actually going down, it opens, and that's where the intake is going to be of the fuel and the air mixture. And then there are injectors in there that they inject fuel in. And when it's compressing now, that closes and opens another one actually for the exhaust. After the whole cycle is closed, after the whole cycle is completed, we're back to point A. Then it opens to get rid of the carbon dioxide and the water that is basically coming from the chemical reaction. Okay, so during that stage, again, we're going back to the point in here, to the starting point where we're going to get more gas now. So more mixture of fuel and air. Okay, and that is basically where this whole process is taking place. Typically, PA is the atmospheric pressure. It's 1 atmosphere. So when the valves open, in this case, we're dealing with the atmospheric pressure, which is normal stuff. But then when it closes, then we have different pressures going all over the place. And then when it opens again, in that case, PA is back to atmospheric pressure, the atmosphere of the outside, basically environment where we are in, where the engine is operating, okay? And typically also this temperature at least is room temperature. So that happens at 300 Kelvin. But then when this starts to compress, now the temperature starts to change. So it's no longer the same temperature. As a matter of fact, there's a very, very important point in here to remember, which is the temperature. This temperature is part of, this line is part of an isothermal. We're going to call it T hot. And this line is of an isothermal that is going to call it TC. But there is a bunch of other temperatures. There is a temperature in here at TB, which does not cross with anybody. There is another temperature in here on point C, and there are other temperatures in between them. But the highest temperature possible is at T hot, and the coldest temperature in this case, at least in the part of the process, the cycle, the closed cycle, is TC. Do not include this one in the calculation because that's going to give you nothing in there. It's not participating in the calculations in here. So this is the TC that we're talking about in this diagram. Okay, so that is the T hot. So this is actually where the actual combustion is, the highest temperature you're going to achieve at this highest pressure, and that is actually where you're going to get the lowest volume, because PV equal to nRT. So in this case, where you're going to get the highest temperature, that is where everything, all the action is happening. So if you're an engineer building an engine, this is basically in a nutshell. Okay, we still have about 5 minutes, and I don't think that we can get into the fun parts of this problem. So what I'm going to do is stop it in here. When we come back next time, we're going to find the efficiency of this engine. And then we're going to go into a Carnot cycle, okay, using, I did not put the writing for it, but I'm assuming that you guys, we're going to leave that to Monday of next week, where we're going to actually put this second law in words and what it means, and then how this engine, for example, or any engine for that matter, compares to the Carnot cycle, because we're going to do this calculation again for Carnot cycle, and we probably will do it. So this is actually problem 47. I may not do problem 47 because it's already, I mean, probably we're going to throw in the numbers from problem 47. We'll do it. We'll do it. Okay, how's that? Sorry about that. Anyway, the point being in here is we're going to do also Stirling engine, which is actually part of the problems that are fun. And I'm going to demo actually for you Stirling engine, and then we will calculate the efficiency in here, and how it compares to Carnot engine. This is part of the exam that is coming in, the midterm, part of everything else. What you need to know up front, I mean, this is no secret, that no matter what happened, no engine can be more efficient than Carnot engine, no matter who you are. Even if you are the smartest engineer working for the best company out there that builds engines for whatever you think of, if you're going to be putting an engine together, you cannot beat Mr. Carnot. 1820s. It could be your great-great-grandfather, but nobody can beat him. Okay? Isn't this amazing? What do you guys think about this? Stuff have to do with engines. Or a lot of you are thinking, let me pass the class and I don't care. That's acceptable too. Okay, that is fine too. Okay, okay, very good, thank you. Okay. Yes, actually it's fascinating stuff. I mean, sometimes I think I'm smart, but then when I think what these people did, it would never have occurred to me. So I must not be that smart. Okay, so that's really, you're right, you're absolutely right. I mean, person has to be humble in front of these people who have done a lot of things for us, and we're using their work. And here, Mr. Carnot did a lot for us, and he actually was never really credited for the invention of this branch of science, which has applications everywhere. But actually, he was one of the people who get the whole thing going. Okay, so I'm going to stop the recording right now. And I will see you guys in the afternoon. Okay, so we have an important lab, so hopefully to see you at 2 o'clock there. And after that, we're not going to meet again until a week from today.